Howdy, everyone. I hope you've been doing well. I'm sorry for the crazy week that we've had, but anyway, I think things should be back to normal after this. So I'm going to record basically two lectures, a total of 100 minutes, and that should get us back to schedule. So this should be available to you sometime by late Saturday afternoon. Sorry if it's a rush for you to watch it before Monday. Today is February 13th, and it's the day before Valentine's, so I think it's appropriate to maybe give you some useful information. Some of you ladies may be uh, romantically involved with potential husbands, and some of you potential husbands may need to get some ideas of how to be good husbands. So I wanted to start and give you a view of the Husband of the Year awards. And so we start with just honorable mention. And so you can see the United Kingdom. This guy is really nice. He's probably got her bicycle there shielded under the tent, so it would not get wet for her. So that's pretty good. So a little bit ahead of Canada was the US, so you can see that she no doubt wants to row, and he's letting her do that. And we go on to Poland. So he's got an umbrella for himself, and she gets the bottles. It's actually customary, quite common in European countries to have people drink a lot of bottled stuff, including water. So when we lived a year in Germany, then people were very commonly ordering Sprudel, which is their carbonated water, and we got used to drinking that also. And third place, so here we go with Greece. And we got a runner-up, Serbia. So they're getting a nice ride while husband no doubt has to drive, and here's probably another poor husband having to walk. And the winner is the Irish, so he's even holding her hand, and they both got their own bottles to carry. Okay, so anyway, I sure hope this recording is working, so I don't have any student reactions, unfortunately, so I can't tell if the whole thing is going to just disappear after I do it all. Okay, so let's go on to PChem. And where we stopped is we were looking at the actual quantum mechanical solutions for the hydrogen atom. And we looked at the radial functions, and we looked at the y functions, which gave us the shape of the orbitals. But the one thing that was strange was if we took the probability function psi squared, it looked like this. This is r in a naught units, a naught being that Bohr radius of about half an angstrom. And psi squared had a maximum at 0, so it would imply that you would have the most electron probability right at 0. The problem is that at 0 radius, there is no volume to put the electron in. So the electron has to go outside the radius, and the larger the radius gets, the more probability there is that that electron will be near that outer shell of that radius. So what we introduce is something that we're going to wind up calling the radial distribution function. But to see how we get there, we're kind of going to look at it in a calculus term. We all learned that 4/3 pi r cubed for the volume, but what you might not have learned in solid state geometry was if you want the thickness, or sorry, the area, let me try again. If you want to have the volume of a if you want a volume of a disk around the center with thickness r, its volume would be 4 pi r squared and then the thickness right here. If we write it in calculus terms, then we write it as a dr, as an infinitesimally small thickness, so we can take that into account. Anyway, the key point is the probability is not only going to be proportional to psi, as we said before, but you also have to add in 4 pi r squared dr. Well, the dr we don't have to worry about, since that's just for the purpose of if we want to integrate or something. But we're able to write the distribution function then in this form, 4 pi r squared psi star psi. So this will be our so-called RDF. And this is based on which our probabilities are defined. So this is what we have here, RDF for the 1s orbital. If you look at how this function varies, it actually starts at 0, as it has to, because that's where r, the distance the electron is away, is 0. Then it builds up because your volume keeps building up faster than what the wave function is going down. Then we hit a maximum point, and then it comes back down and goes down. Misan. We don't get it? All right, 60 up and it's 70, but it's set on 70. I'll put it to 71. All right. All right. I guess I thought they left you like that. Okay. Had to pause that for a little bit. Sorry about that. But anyway, this is the RDF, which is going to give us the best picture of where we expect to find the electron much of the time. Now keep in mind, typically in a system of atoms or whatever, you have jillions and jillions of atoms and electrons. So this will actually be a distribution with a lot of electrons. At this point, the maximum, some down here, building up at these different R values, but it can extend out to at least many A0 values. Theoretically, you have to go to infinity before it dies out. Okay, just made the screen a little bit bigger so we can look at that. All right, as you notice, I've indicated that the maximum probability is A0. This is the Bohr radius. This is what Bohr himself thought would always be the radius. And when they draw pictures in high school laboratories of atoms, they typically then put the electron nominally at 0.53 angstroms away from the nucleus. Okay, well, how do we know this is A0? Hopefully everybody is sharp when you read this and to think about it. How do you find a maximum of any function? Well, you take the first derivative and set it equal to 0. So here is our RDF. We're going to take the first derivative of this and set it to 0. The 4 pi, of course, we can throw out so we don't have to worry about it. And then the rest of it is just the math. So we have an R squared from that. And then we also get an A0 from the normalization, but that comes out in front of the derivative. and the square of the wave function is e to the minus 2r over a naught. The wave function itself, as you might not remember, is e to the minus r over a naught, so squared it's e to the minus 2r over a naught. And here's a little reminder for you. If you have e to the 8th power squared, it's summing the exponents of the two terms. And so it's e to the 2a power. All right, so this is what we have to take the derivative of. And keep in mind, this is going to give us minima and maxima. So we'll first take a derivative of the r squared, 2r, fix the second term. Then we'll fix the r squared, take a derivative of the second term. This is what we have to solve. We can factor out the e to the minus 2r, and this is what's left from the rest of it. Notice that it can be 0 if e to the minus 2r over a naught is 0. So we see that r at r equal to infinity, we will get a minimum. But you got to go all the way out to infinity if you want the probability to totally die out. I always used to tell my classes that electron probabilities extend to infinity. Therefore, everyone was sharing their electrons with their neighbors as they sit in class. But I think I mentioned to you that I had this very bright 14-year-old taking our physical chemistry course. And he did a calculation for me, said that's not going to happen because the probability of being out there was something ridiculously small, like 1 in every 10 to the 80th electrons would be at the distance of, say, a foot away, whereas a human body doesn't have that many electrons. So I thought it was a nice story, but it no longer works. Okay, the other term we have, you can see you can factor it into r, and 1 times 1 r times 1 minus r over a naught. R can be 0 as a solution. That's a minimum. We've already seen that. That's being at the nucleus. And then the final solution will be 1 minus r over a naught is equal to 0. If you solve for that, you get r is equal to a naught. So you can expect when we get to exams, first hour exam or the final, you might see a problem of asking you to find the most probable distance for an electron for a particular orbital. So it would probably be for hydrogen, but it wouldn't have to be the 1s orbital. It could actually also be for helium plus or lithium plus 3. So make sure you know how to go through this. But it's basic elementary calculus that you need to go through to get the answer. Okay, so knowing how we do these things, let's just look at what the radial distribution functions look like, and then r squared times r squared, capital R squared. I said radial distribution function, but capital R is the radial function, and on the right, this is the radial distribution function, missing the 4 pi, but since that's just a constant, the relative numbers really don't have any significance. In other words, we can drop the 4 pi. Okay, so this, as we saw for R, it looked like we're going to have a high probability at 0, but when we put in the volume term, we see that the wave function hits a peak at 1a naught, namely the Bohr radius. Okay, next we have the 2s orbital. I pointed out to you it had a node in there. And you see now this is the distribution that you have. There's a small region. This shows that the electron can actually be just as close as the 1s. Then there's a point right around 1a naught where the 2s electron cannot be. Then it peaks out somewhere. I'm not sure exactly what that is. I guess it must be 5a naught as such. The 2p orbital I know peaks out at 4a naught. So it's kind of funny. 1s is at a naught. The 2p is at z squared a naught. So I don't mean z squared, I mean n squared. So it's 2 from the 2p, so this comes out before a naught. And then if you go to the 3D, this comes out to be 9A naught. So you can ignore all that if you want. But anyway, that's the way they come out to be. It's not that the 2s winds up being 4 times away, it's the 2p. And then it's not the 3s or the 3p that wind up 9 times farther away, but it's the 3d. If you remember the Bohr model, he predicted 1 for n equal to 1. He predicted 4A naught for n equal to 2. And then he predicted 9 or 3 squared for n equal to 3. Okay, well, hopefully you can digest this and see this is a pretty good idea where electrons would be. This is strictly accurate for the hydrogen atom right here that I'm showing you. We're going to spend only a little bit of time on larger atoms, but basically they will have similar orbitals to hydrogen, almost always, or I could even say always, because of the higher nuclear charge, the electrons will be pulled in much more tightly. So a 1s electron in, say, cadmium, instead of being at A naught, it might be something like 0.2 A naught because of the, whatever it is, 30 or 40 protons that are in the cadmium nucleus. But the general shapes of the orbitals will be pretty much the same. And then you're going to have distributions of the electrons moving further and further out as you're going to the N2 shell, to the N3 shell, N4 shell, and so on. Anyway, I strongly recommend when you go home, look at this again, think about it, and just try to get a feeling for what electrons are doing. This only goes through the 4 shell, but notice it's weird. You have 1, 2, 3, 4 regions of probability with nodes in between. And so one is tempted to ask, well, if you have an electron here in the 2nd region, how is it going to get to the 4th region? And here again, these are time-independent pictures. We're not considering the time dependence of the situation where the electron is able to fly around and go from one orbital to another and then come back in a different region for the 4s orbital. But a snapshot picture of electrons in a 4s orbital would put them according to these probabilities that you have there. Okay, well, we haven't talked about d orbitals. You learned about these in freshman chemistry. If you were like I was, then the d orbitals seemed weird. We had 3 equivalent p orbitals, and they all looked alike, but just pointed in different directions, x, y, and z. But when we went to d orbitals, we had 3 that kind of looked alike, and then we had 2 really weird ones, the dz squared and the dx squared minus y squared. And in freshman chemistry, I never got an answer of why these 2 should look the same. Well, let me first point out that this is not what the quantum mechanics gives you as answers. So when you solve the equation, you get the d plus 2, d plus 1, d0, d minus 1, and d minus 2. And these subscripts correspond to what the m sub L values are. So remember, for the p orbitals, we had m sub L plus 1, m sub L 0, and m sub L minus 1. Those were the 3 orbitals. And then we converted them to px, py, pz, but we lost the definition of what m sub L went with each. So to get these orbitals, we have to take linear combination of these 5. The dz squared, as it turns out, looks just like the d0, but the others come from these linear combinations of d1, d minus 1, d2, d minus 2. So we don't need to go into that. If we go into f orbitals, we would have a total of 7 m sub L values for plus 3 ranging down to minus 3. And then if you really go into the newest elements that people have made, then you have to worry about g orbitals and such. Important point to remember, and I've said this quite a few times, is for the hydrogen atom, whether you have s or p orbitals or d orbitals, they do not affect the energy. Only the principal quantum number affects the energy. This is not true for larger atoms. In freshman chemistry, you learned 1s2, 2s2, 2p6, etc. And you learned that the 2p orbital was higher in energy than the 2s orbital. So when you start having more than one electron, you have interactions between the electrons, and the shapes of the orbitals do make a difference as to the energies. The shapes, of course, come from the angular momenta components, and so it's the interaction between angular momenta that gives you the different energies that you have. Okay, here's some pictures of orbitals, and I'm showing you the ones that come out directly from the quantum mechanics. So when I have s orbitals or the 2p0 orbital, which is also the 2pz, I can show them to you. This diagram does not show, for example, 2px and 2py, because these distributions are not as validly generated. Anyway, as you know, orbitals are spherical, so a 1s orbital is spherical. And what this diagram wants to show you is where is the density of these orbitals. Each concentric circle contains 10% of the probability. And you can't really see the lines in the copy that I have here, but the dark shaded area contains 40% of the electron density. Then if I go to the next line, I'll have 50%, 60%, 70%, 80%, 90%. So when books typically draw orbitals, the goal is to show the volume that would contain 90% of the probability. But to try to get to 100%, I'd have to take this all the way out to infinity. It gets very, very, very small quickly. Even if you go something like 1/100th of a millimeter or something, the probability would be exceedingly small. But most of the electron density is here. Notice when I talk about electron density, it's kind of strange because we're just talking about one electron distributed like this. So maybe that makes more sense to you now that we've talked about where the probabilities of an electron are. But an individual atom, you can't know exactly where that electron is, thanks to Heisenberg showing us that we cannot do that. Okay, anyway, 1s orbital, not a big surprise, no nodes. Here's the 2s orbital. There's a node in here, kind of a fairly probable area. And then past the node is not as probable, but then the higher density of probability is out at these higher values. And then you have to go to further values to get the 90% as such. And here is the 3s orbital. Okay, I'm having trouble reading my own notes. 3s orbital, and you can see it has 3 regions of probabilities, tighter here, but again, then this is further out where it goes. Okay, so this is one of the p orbitals. As I said, the 2p0 and the 2pz are the same. We've seen often that they're drawn more or less like this. And again, there's an area that's pretty tight that contains 40% of the probability. This now is the 3p. It starts getting cuter, I think. There's more nodes that you have in here. But notice even in a 2p orbital, the electron can sometimes get in tighter or as tight as maybe a 1s orbital. So the thought that the 3s orbitals are necessary, or 3p or 3s orbitals necessarily have the electrons further out than the 1s electrons isn't always true. So that's a concept known as penetration, that outer electrons can penetrate inward, and so you can get effects you might not have expected. And then here's the final picture to look at. So these are more quantitative than you typically see in textbooks, like especially freshman books, so get an idea of what these are like. Remember, in this orbital, which is also called the DZ squared, this is kind of a concentric circle, like a donut around here. So it's pretty weird what Mother Nature decided to do in shapes of these orbitals. Okay, one of the things that we are interested in, and especially will be when we get to talking about spectroscopy, is the topic of selection rules. And we've talked quite a lot about the atomic spectra of hydrogen, and I'm going to give you selection rules for hydrogen and then tell you that they also apply for larger atoms. For hydrogen, it doesn't seem to make much difference. But selection rules come from the Schrodinger equation in the time-dependent form. And they will tell us which transitions you can have, the change from one energy to another. And what we're going to find is, first of all, we always have delta E is equal to h nu. We know the energy difference. This is related to the frequency by Planck's constant. So this you should go to sleep with, and it's just a fundamental aspect of any time you're looking at spectroscopic things, be it vibrations, rotations, atomic spectrum, or whatever. I don't think I mentioned this before, but if I have, it's worth mentioning again. The other selection rule comes from this. This is the intensity of a spectroscopic transition, and it can be either emission or absorption. It turns out either direction is just as probable, but if we're sitting here on planet Earth, most of the time we are looking at absorptions because atoms tend to be in their lowest energy states. And so if you shine light into them, you can drive them into upper states. If you find some way to excite them into upper states, then they can emit back some of the energy. But each process is just as probable, but usually the populations at lower states, the number of molecules at lower states is much higher, so typically we're looking at absorption. Anyway, we find that intensity is proportional to the square of what's called the transition moment integral right here. And the important thing is that you have to know the wave functions for the beginning state, which here I'm calling the initial state, and then the final state, which I have F here, size of F. And in the middle is something called a dipole moment operator. Spectroscopic transitions occur when the light that is coming in plus minus as a wave interacts with a dipole moment within the molecule. So this takes care of that. And that dipole moment in the molecule is going to be pointing in the X, Y, or Z direction, or possibly all of them. So you might need to do this calculation in 3 dimensions. But all we care about is that you either put an X, Y, or Z into this integral and try to solve it. When you get done with it, if you get I equal to 0, it says the intensity is 0, we say it's a forbidden transition. So you can't get any frequencies out either from emission or the atom will not absorb anything when you shine light into it. If it's anything other than 0, greater than 0, then we call it an allowed transition. But note that the intensities can vary all over the place because these integrals can be tiny, 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 or if we get to electronic transitions, which are responsible for giving us the color in the universe, then they can be really intense. So let's be thankful for that we get a pretty universe around us to look at. Okay, so what is the so what for the hydrogen atom? Well, the so what is it almost doesn't matter at all. For a hydrogen atom, delta N can be anything. So you saw we had the Balmer series, the Lyman series, the Punt series, et cetera, et cetera. So we can go from any N to any other N. But the selection rule is delta L is equal to plus or minus 1. So you cannot go from an s orbital to an s orbital, or p to a p, or a d to a d. From a p orbital, you can go to an s orbital or a d orbital. From a d orbital, you can go to a p orbital to an f orbital. So this is important for other atoms where the energies get to be different. And so I'll show you an example of that in just a little bit. Okay, I'm going to skip over a couple of pages that I'll come back to. And just to show you how this works, here's the picture for the hydrogen atom. And these are the transitions that you're getting. But notice that here, for example, this arrow from the 4p orbital, this has exactly the same energy as the 4s orbital. So it doesn't really matter for hydrogen that it's a p to s transition that you can have. It's still exactly the same energy change because the orbital energies don't change as a function of s, p, d, f, and so on. But you can see you can only get to s orbitals when you start from p orbitals. Okay, I'm going to pause this a second. Okay, I'm going to start it again. I want to make sure I could find this page. This shows you what's going on in a larger atom. And I'm sure this is more than you wanted to know. But first of all, you'll see some things called term symbols here. This is stuff that I said we skipped over in quantum mechanics based on Russell-Saunders coupling. Here's an explanation of what the term symbols mean. The capital letter tells you what is the orbital angular momentum. The subscript tells you the total angular momentum. And then the multiplicity, it tells you how many unspins you have, 2s plus 1 up here. So spin 1/2 for each electron. So if you have a 1 unpaired electron, it would be 2 times 1/2 plus 1. And so that's what you would get right here. Okay, so I've said physicists like this a lot, but this then shows you what kind of diagrams you have. So here are energy levels with orbital angular momentum of 0 or s. So these would be s orbitals that you could have. But you look at all these cross arrows, and just by the way, if you didn't notice, it's for the sodium atom emissions that you have. And so it makes a big difference whether you're in an S level or a P level or a D level or whatever. So there's lots and lots of transitions that you get. I think most of you are familiar that streetlights might be sodium vapor lamps. They kind of have an orangey glow. They're rather cheap to make and very efficient to use. A lot of what you're seeing there are some of these transitions that you have here. You use electronic voltages to kick the sodium atoms into upper states, and then you can generate the emission. Something that I learned just a few years ago is the reason that comets are orange is also due to free sodium. So that sounds really weird because, as we know, comets are basically big ice balls. And you would think if you have a lot of ice and you have sodium atoms there, you'd have the same effect that you saw in high school chemistry when somebody dropped a piece of sodium in the water and it released hydrogen, probably ignited the hydrogen, and the sodium went to Na plus and stuff. Anyway, there could be a lot of interest in atomic spectra of this type, but we leave that mostly to physicists to think about. Okay, so let's go back to where we were. But before we go on to larger atoms, let me tell you about an approximation technique that is generally used when we have to get to larger systems. The hydrogen atom, we could solve it exactly, but even when we go to the next largest atom, helium, we have to use a numerical method, and generally it would be a variation method. Some books call it variation method, some call it the variational method with an AL, but either way, it's the same thing. To see where it comes from, remember we can write our wave equation. The Hamiltonian working on psi gives us the energy levels times psi. Hamiltonian, you remember, has the second derivative terms in it, plus a potential energy term. And so that's basically the full Schrodinger equation. Okay, well, let's take this equation, multiply it by psi star, and so this is what we have. And notice capital E is a constant, so we can pull it out of the formula. We solve for E, and this is what we get. Notice that if we are working with a real accurate solution to the Schrodinger equation, the denominator will be normalized. So the denominator just goes out. And then all we have to do is solve what is up here. And we've seen the case that sometimes the H psi gives us instantly a constant E, and we can get to what that value is. All right, well, that part we've done before, but we're now interested in an approximation method. And I keep being thankful to mathematicians that have figured this out. And I'm not sure who did this one, but this is an amazing technique, as I will show you. If we don't know what the actual wave function is, and this would be the case for the helium atom or the lithium atom or the sodium atom, we have to have some kind of approximation method to get there. So the method typically used is we guess a psi. So that sounds pretty iffy. You don't want to just guess that it's x cubed or something. But we want it to be an intelligent guess, and so that we're going to call a trial function. And what can be shown is that if you calculate the E, after you put in a trial function, the real value of the energy, the E that you calculate will always be greater than the real value. If you put in the accurate wave function, you will get the real value, but otherwise the calculated value will be greater. So as you might expect, the better the guess for psi, the better or lower the E calculated value. So the methods that are generally used by computers is you try very sophisticated trial functions, you find ways to get the lowest possible energy out of it. The lowest possible energy then you think should be very close to the real value. And unless the problem gets really humongous, like thousands of atoms or something like that, and if you're willing to take computer time to do it, you can get the answer to 7 or 8 decimal places and virtually consider it to be the right answer. Okay, just to show you how well it works, here's our square well potential. This is exactly what we did before, except I have my right wall at little a here instead of capital L. Potential energy infinite outside the box, potential energy inside the box. And you remember our boundary conditions have to be at psi of 0 has to be 0, and psi at the right wall here, it's a, also has to be 0. So notice that I'm going to guess this function not blindly. I'm going to stick to the boundary conditions that we have. Make sure you remember about boundary conditions. I love to ask about that on examinations also. So the wave function has to be continuous. So outside the boxes, it's 0 because there's no probability there. So when we join at the wall, the wave function has to be 0. Okay, so the trial function I'm going to choose, I think this is the simplest polynomial that I can use. It'll be a normalization constant times x times a minus x. Now keep in mind, just to show you below, this was a real function. So we know that this is not going to be all that great a guess. I'm trying to use a polynomial to represent a sine function. But let's see how it works out. Okay, our rule here says that we take h psi first, and always in these equations you take the operator first. So that means you take the second derivative of psi and multiply it by minus h squared over 2m, and you solve it, and what you see that you get, I'm trying to see where okay, here are my derivatives. Here's d psi dx, and here's d squared psi dx squared. Notice it comes out simply be minus 2m. You have to make sure you carry your normalization constant along. Okay, so we plug in for the second derivative. The minus signs cancel out, and we get nh bar squared over n. M. So this is what we have to solve. We integrate from 0 to a. We know the wave functions are 0 outside of this region. So I'm not going to go through this. You should be able to do integrations of polynomials. If you are rusty at that, I recommend you go back, but it's pretty simple. It's the first thing you would have learned in calculus, maybe third week or something like that. Anyway, you do the integrations, and so this is what you have to integrate on top, and this is what you have to integrate on the bottom. So notice you'll have an ax term and an x squared term here. Here you'll have an x squared term, and you'll also have an x to the fourth term. So this is, and a cross term too, which comes out x to the fifth. So this is what you have to evaluate. Confirm for yourself you can do this. When I do it, you get a 2 pi squared in the denominator that I didn't write out, and you get the answers 0.1267 times that. If you look back in your notes, you'll see the answer is 1 over 8 of h squared ma squared, or 0.1250. So you should be impressed that this is less than a 2% error, making absolutely the worst guesstimate that I could get, but I'm still getting a very good energy expression. So this shows the power of calculating the energy. Now, if you graph this function, the trial function versus the real wave function, they won't look nearly as good. So here I'll try to show that here. So the real function is nicely symmetric about the center. The guess function is a little bit to the right. So anyway, if one wants to get better, then you have to use better trial functions. And I'll show you just how to do that in a second. Okay, so I'm just pointing out that we have, in the real case, if you do the Hamiltonian on psi real, you immediately get the real energy levels for that particular wave function. Notice we're doing this for only one of the quantum states of the particle in the box, which happens to be the lowest level. For a trial function, unless you're phenomenally lucky and guess a function that is actually the solution that has never been found, you're not going to get the exact calculated energy level. All right, well, as I said, if we guess a better trial wave function, we'll get an even better result. So I should have probably cut and pasted and put this on the previous page. So this is nicely typed out. I've used this in a lecture that I have. We get to 0.1267. And again, mediocre guess gives us a pretty good result. So let's try a little bit harder. And instead of having just the one term that satisfies the boundary conditions, let's square both of these terms. So you'll see that this would help the situation. And the way we do this is we calculate what the energies are as simultaneous equations in terms of coefficients C1 and C2. After we get our simultaneous equations for E, then we take the derivative of E first with respect to the first constant, and then with the second constant. And then we get two simultaneous equations that can be solved. This is generally called the secular determinant. If it's a 2x2 problem, you don't even really need to set up a determinant. But in real computations where you might have 100 or maybe even 10,000 terms, then you really need the computers to come help you. You need linear algebra techniques and everything else like that. But that secular determinant can be solved, and as you can imagine, if you're using hundreds or thousands of terms, you're going to get these answers very, very, very accurately. So as we go on, I just want you to be aware that there are powerful techniques to get us to about where the right answers are. Okay, so we're pretty much now covered hydrogen, spectroscopic rules, and the methods that need to be applied if we start looking at larger systems. And we need to be aware that these can't be solved exactly. Now, what I do expect that you would be able to do is write the Schrodinger equation that will work for these larger systems. Later on, I will, let me see if I have something here. Okay. Later on, I will justify what I'm about to do here. We're going to do the Schrodinger equation for 2 electrons on the helium atom. Later on, I'm going to tell you about something called the Born-Oppenheimer approximation, which says that when we solve it, we can ignore the slow nuclear motion. So the first 2 terms here are for the kinetic energies of the electron, and we're saying the kinetic energy of the proton doesn't matter. Also, if we put in a similar term for the proton, it would have a very heavy mass here in the denominator that would make the proton term drop out. Okay, I need to pause again. Okay, so I took a little pause. Let's now continue talking about larger atoms. Again, I want to point out we're only interested in electron energy. So whenever we talk about 1s2, s2p orbitals, the nucleus is just sitting there hanging on to the electrons, and we want to know what the electron functions are and what kind of energies they'll have. One thing I do want you to be aware of and be able to do is write the potential energy function. So the potential energy for electrostatic attraction or repulsion is the product of the charges divided by the distance between them. So here in helium, we have the +2 charge, and here's electron 1 at a distance r1 away. So this nucleus has a +2 E charge. The electron has a -single E charge. So it's -2 E charge is the product divided by R1. Second electron is attracted similarly, +2 E charge attracting a -E electron. So we have minus 2 e squared over the distance between. And then the repulsion between the electrons is R1, 2. Or it's the distance between the electrons is R1, 2. And the repulsion is plus e squared over R1. So it's minus c times minus c gives us plus e squared over R1, 2. Keep in mind that negative values or low energies are good. Everything in nature wants to go to its lowest possible value. So if we have minus signs, that means it makes systems more attractive. Plus signs makes them less attractive, or we have repulsion. Okay, so what we're going to do here is just kind of show you how the quantum mechanics evolves. So first, we're going to ignore the repulsion between electrons. This is what destroys the analytical solution for helium on the Schrodinger atom. So let's see what kind of energies we would get. So we're going to have 2 electrons, and we'll say the Hamiltonian for each is either H1 or H2. For electron 1, this will be the Hamiltonian. In other words, this term plus that term. So electron 1 here, electron 1 from the potential energy. So this is what we're going to solve for electron 1. Electron 2 looks exactly the same, except the kinetic energy term is for electron 2. And here is the attraction for electron 2. Well, since these are basically 1 electron systems, so they're like an He2 plus ion, where each electron is ignoring its neighboring electron. We then would have exact solutions for these individual electrons, which look just like hydrogen. The main difference is now our Z value is different. And as we talked about before, if we had helium plus, then the attractive energy, or the total energy, would be Z squared R sub H. R sub H, remember, is 13.6 electron volts. And so what we would have here is 4 times that. And then since there are 2 electrons each, which would be 4 times, we would end up with 8 R sub H. We would get minus 108 minus 0.8 electron volts as the overall energy of the helium atom. Well, it's not nearly that low, and that's because we've just ignored the repulsion of that electron. The exact value, which has been measured and comes from correct theory, is minus 79. So you can see that's something like 40% too low. So way too low. Maybe it's only 30%. It's way too low. Now, if you take the same approach and you just throw in the repulsive term and throw that into the integration, you get down to minus 74.8. But that's still not a very good number as compared to the minus 79. And this is based on the variation method, where the calculation energy is greater than the exact energy. So minus 74, of course, is greater than minus 79. The absolute value is smaller, but since it's negative, it's greater. So that's what one would wind up with. Now, some bright student a few lectures ago said, well, what about the Pauli exclusion principle? Well, this is going to make the difference in the ballgame, but this is not what you might have expected when I tell you about it. First, let's jump to Wikipedia and see what Wiki says about it. It's a quantum mechanical principle formulated by Wolfgang Pauli. Now, notice this is right around the time Schrodinger's coming up with his formulas. In its simple form, for an electron in a single atom, it states that no 2 electrons can have the same four quantum numbers. N, L, and M sub L. If they're the same, M sub S must be different. So this is what requires that you have to have opposite spins. And this is typically what you learned in freshman chemistry about these quantum numbers. The specific formulation by Pauli is that no two identical fermions, fermions are particles with half integer spin, like an electron. Fermions follow what's called Fermi-Dirac statistics. Fermi was an Italian scientist and Dirac was an American scientist. And so they get credit for the name fermions. But so they came up with the fact that they could occupy the quantum state simultaneously. But the more rigorous approach for getting to this was that the two identical fermions, the total wave function has to be antisymmetric. So up to now, we've been writing the wave functions without the spin part. So we had the angular part and the angular orbital part, which has given us M, L, and M sub L, but we haven't talked about the spin part. So as suggested by Wiki, this can get to be nastier and more sophisticated, but let me show you how it works. So in freshman chemistry, you learn you can have spin up or spin down, and if you put two electrons into the same orbital with the same M sub L value, they have to have different parts. They either have to be up or down. In our nomenclature, we're going to say alpha represents spin up, beta spin down. So if we have two electrons in the same orbital, one possibility would be to have alpha 1 or alpha 2. So that would be both spins up. We're going to see that doesn't work, but I'll show you why. Then we could have beta 1 and beta 2 both spins down. That also doesn't work. We could have alpha 1, beta 2, or we could alpha 2, beta 1. Well, either one of those sounds okay, but it's too rigid because you're forcing each electron to have a certain spin. And if you're a free electron and you're going into that orbital, it doesn't care if it's up or down. So one could be either 2 or 1. So I think both of these models could work. So it looks like we need a linear combination of these two possibilities to make it right. Okay, so there are two ways to combine them. We combine them with a plus sign that looks like this. So we have possibility 1 up, 2 down, and also possibility 2 up, 1 down. So this is a linear combination of possibilities for our function. The other possibility is we can combine them with a minus sign. And I guess all I can say is don't worry about what it means if it's plus or minus. What it's going to mean is that the minus sign one is going to mathematically make it work because it's going to give us a function that would create an antisymmetric function like Pauli demands us to do. So this is pretty complicated. Don't be upset about working out all nitty-gritty details, but I'm hoping you appreciate that it's more than just saying you can't slip two electrons into the same orbital, or that no two electrons can have all the quantum numbers the same. All right, well, it turns out that the orbital part of the function here, if you look at it, is symmetric with respect to exchange. If I change 1s1, 1s2 to 1s2, 1s1, it looks exactly the same. So if I change the electrons, this part of the function doesn't change. So this is symmetric with respect to exchange. My choices 1, 2, and 3 up here are also symmetric with respect to change. So no matter what I do, the function looks exactly the same. But if I put this one in there, it will change sign. So notice if I put a 2, 1, 1, 2, we wind up getting exactly the negative of that. And that's what we mean by a function being antisymmetric. So to make the quantum mechanics work for systems like helium now that have two electrons that have to go into the same orbital, we have to worry about Pauli. And when Pauli comes along and you put in good enough angular orbital parts and so on, you can get a much, much better value for the whole thing. Okay, so these next couple pages I stuck in just to sort of give you supplementary material to show you how calculations work. You won't really be tested on this material, but I will come back to the concept of shielding, which is quite important. But the first basic quantum mechanical technique that was used is called the Hartree-Fock self-consistent field method, or SCF. Sophisticated calculations these days kind of scoff at this and say, if you give me a Hartree-Fock results, I'm not interested. You might be 5% off. It's going to be a bad number, and we don't like working like that. But just to give you an idea of how it works, we're going to assume that each electron sees the rest of the system as similar to a hydrogen nucleus. So we're going to assume here an example of lithium, which has 3 photons and 3 electrons. If we're looking at this outer 2s electron, this inner part is just going to act like it's hydrogen-like. And so we're going to look at 1 electron being attracted by 1 nuclear system. But this electron is not going to see a +3 charge because there's 2 electrons around it. So this brings up the concept of shielding that we'll come back to again. But the concept of shielding is that the 2 electrons here won't totally cancel the +3 charge, but they will do a pretty good job of canceling it out. So what calculations have to show is what effective charge is this outer electron going to go. So again, just to summarize, if these 2 electrons did nothing to cancel out the charge, this outer electron would see a +3 charge. But since they're doing a pretty good job of canceling out the +3, this electron will see a 1.28 charge. If they totally canceled out as much as they could of the +3, then this electron would see a 1.0 charge. So most of that 2 by these 2 electrons, the -2 charges, is effective in canceling out the +3. So the way Hartree-Fock works is you first do calculations to determine what your wave functions and your energy levels look like for each of the electrons, one by one, using these kinds of rules for effective charge. After you get a result, then you can get better effective charges, and you keep going around in a circle, and you see what kind of result that you get. So that's the general feature that we have right here. Okay, so what I just showed you was the Hartree part, and then the Fock part applied the Pauli in principle. So Pauli, of course, is representing the electron spins. And so if you do Hartree-Fock together, you calculate energies accurate to about 1%. But as I said, this is still a big error. And theoretical chemists today just scoff at people who have errors larger than 1%. We don't want to even hear about it. So spectroscopically, 1% of 109,000 wave numbers is 1,000 wave numbers, and you would be way off in doing your spectroscopy. Just a brief comment about that. You get past that 1% by using correlation energy. I'm sort of thinking to myself, how much should I tell you? There's something called CCD, coupled cluster, single domain calculations, and so on. Anyway, you do correlation energies, which calculate instantaneous electron positions and how they affect each other in a broader sense to get the answers. Okay, so here are some general results that we get from these kinds of calculations. Yeah, these are where the electrons are for an argon atom now. Argon has 10 electrons, so it's 1s2, 2s2, 2p6. It still has the outer orbitals, and here's the 3s orbitals shown. But you can see where the electrons are. So the 1s electron is really tight. Here's the 2s electron. Oh, wait, sorry. Here is the 2s electron, and you see it's got that node here and a little area of probability. That's called penetration because it's getting into the range of where the 1s electrons are. Then the 2s electron does not have any nodes, but you can see it moves out to something like 0.5 A naught. Remember, I pointed out that when you get to larger atoms, argon now has 10 protons. So its 1s electron looks like it's about 1/10 of a Bohr angstrom rather than half a Bohr angstrom away from the nucleus. So it's sucked in 5 times closer. The 2s electron now looks like it's getting closer to where the 1s was for hydrogen, similar for this is 2s, similar for the 2p. And then if you excited an argon electron to outer orbitals, then they would wind up moving further out. So hopefully this gives you a general idea where electron density is. This group is called the inner electrons. You learn all about that in freshman chemistry. For students who take inorganic chemistry, they learn about these, but they're generally not considered to be active for bonding. So argon, of course, is considered an inert element. If you took off a few electrons and had something like fluorine or oxygen, nitrogen, then these outer electrons become what you call valence electrons that can participate in bonding. The diagram on the right shows a close-up of the orbitals for n equal to 2. So this would be the 2s electron and 2p electron. You remember I pointed out the node that you have for the 2p and the 2s. Okay, so keep that in mind, especially the concept about shielding, and I'll talk about this more because in my mind, this is the most important thing in understanding inorganic chemistry. Now, chemical engineers and biochemists don't take inorganic chemistry, but if you ever encounter inorganic compounds and look at atoms in inorganic systems, this concept will tell you more than just about anything else. But first of all, freshman chemistry, this is what you learn to write. In fact, you learn that 4s orbitals popped up in front of d orbitals and so on. So whatever the angular momentum quantum numbers are, start making a huge difference when you get to higher and higher orbitals. Okay, well, we already talked about the helium atom, and so the way that I initially presented the calculation is, let's pretend we just have a +2 charge holding on to 1 electron, and so we could behave this as if it had hydrogen orbitals. So that would be a hydrogenic type system. Then what we do is we bring up the second electron and we create repulsion. This electron is then also attracted to this nucleus. These are the quantum numbers that we have. You should have learned all these in freshman chemistry. The simple-minded way okay, so this you should have learned in freshman chemistry, and that's the simple representation. But as we saw, the Pauli principle says it's because of the anti-symmetry of the overall orbital. So I think I will stop the first lecture at this point, and I'll try to work in the second one over the weekend also.